All right, good morning. So today we'll be continuing with our discussion of autoencoders, and this time we'll move towards regularized autoencoders and variational autoencoders. Before that, just from a logistics point of view, the exam 2 results were released yesterday, sometime in the afternoon, so you should be able to go on Canvas and look at the solutions. I also checked the solutions as well. So basically that means that you should see the answers that you have given as well as the actual solutions that are there. I believe for the in-person students, the class average is 76 for exam 2. And it's a little bit higher for the distance learning students. I believe it was like 78 or 79 was the class average. With the median around, with a standard deviation around 13. The maximum was 98, which was the highest score across both the classes. I think it was here in the in-person class. I had gone through quite a few papers and did some manual checking. So there were many instances where some of you, for instance, there was this one question about the CNNs, right? About the activation map itself. The answer was supposed to be something like 120 cross 120, let's say. And some of you had written it like this, and some of you had 120 cross, but there was no space between. It was 120. So the way Canvas works is that whenever even a single space is different between the answers, the provided answers and your answers, it's going to be marked as incorrect. I've tried to go through all of them and try to correct them as much as possible, but if you see in your solutions that the answer that you have matches that is in the solution key, please let me know. Either as a private post on Piazza or via email, and I'll try to correct that as quickly as possible. I don't think there was any kind of a systemic problem in terms of the, there was no bias where everybody had gotten a question wrong. There were a lot of cases where some of the questions were answered incorrectly, but it wasn't prevalent like throughout the class. In fact, the only one I saw was within a true or false question. I believe it was the second question where it was about whether gradient descent can be used to train something that is non-convex. While it was not a theoretical question, it was an empirical question, which basically meant that since we already use it in order to train neural networks, which are inherently non-convex, there's nothing stopping us from using gradient descent and it giving us a good solution, because there's some kind of bells and whistles that we use on top of it, right? Anything with respect to using momentum, using ADAGRAD and all these other methodologies essentially is helping your gradient descent get to the optimal solution even in non-convex solutions. So I believe out of like 70 students across both classes, the distance learning and in person, about 20-25 people had gotten that incorrect. So that was the only question where I saw that about 1/3 of the class had gotten that question incorrect. But apart from that, I think every other question has been answered in a reasonable fashion, I would say. So yeah, just let me know if you have any doubts. Go through the answer key, check your solutions, see if there's any similarities. If there is, just let me know and I'll be able to go through and correct them. Regarding homeworks, again, homework 4 I think was released yesterday as well. So please contact the TAs. They're the ones who are in charge of doing the grading for the homework. So either go visit their office hours or just ask them for a meeting one-on-one if that time doesn't fit for any of you. So regarding the homeworks, they are the people who are in charge, so you should contact them. All right, with that, I think we have quite a bit of things to cover today. If we had to complete autoencoders, which I intend to, by the end of this lecture, hopefully from next week onwards, it's going to be sequence modeling and transformer architecture. So we do want to complete the autoencoder-based architectures today. So where we left off was convolutional autoencoders, which basically you can think of it as a ResNet 18 encoder. So you take the entire ResNet 18 architecture until the final fully connected layer. So that part is your encoder. And the goal now is to convert, is to take these outputs from this encoder and reconstruct your input again. The reason being, of course, is that this is an unsupervised architecture, and the goal is not classification, but rather it is to learn some kind of a representation that is generalizable across different data. It's not just for a single task of classification. Rather, you can construct multiple tasks based on it. So today we look at one important task, which is generating new data. So if you have heard of generative models, it is essentially an offshoot of what we'll call the what is called as the variational autoencoder. We'll do a very quick, a very simplistic review of what variational autoencoders are, and some of the math details are not as essential. The motivations are probably more important in this case rather than the exact math solutions, but we'll come to that in a little bit. Before that, we'll start off with something called regularized autoencoders. And the first word over there, regularization, is something that you have seen in when we did both classification as well as regression. Essentially, regularization is some kind of an additional term that we add to the loss function. The goal is that we don't want this to be a gradient descent to be an optimizer. We don't just want a very good representation on the training data, but then it cannot do anything on the test data. It needs to learn something that is extra, that is different, and that is done via some kind of a regularization. So we want to regularize representations to learn important and complex features without restricting the latent dimensions. So this is the autoencoder that we saw before. We had an encoder that went from data X to a latent representation Z, and from that latent representation, we were able to use a decoder architecture to convert it into a reconstructed version. Now, the hope and goal is that the reconstructed version XCAP is the same or very, very similar to the input data X, and all training that we do for encoder and decoders essentially has to go through this, and we need to come up with some kind of techniques in order to maintain X and XCAP to be as similar as possible. So in this case, you can see the difference of how latent representation makes some changes. Let's say my input data is X, which is your MNIST dataset of 28 cross 28. When I try to reconstruct it based on latent dimension so this latent dimension, let's say, is just a 2 cross 1, a very small vector of just 2 cross 1, you can see that it still is able to reconstruct. The second one here. It still is able to reconstruct some kind of a image based on it. And in a way, this is surprising, right? You have your 28 cross 28 image, which is a 784 cross 1 vector that has been reduced to a 2 cross 1 vector. And now this 2 cross 1 vector is now being again blown back up to like a 784 cross 1 vector, which is a 28 cross 28 image. But even within this 2 cross 1 image, there is enough sufficient information for you to be able to reconstruct the entire data. And you see that when you increase the size a little bit from a 2-dimensional latent space to a 10-dimensional latent space, the results are a little bit better, not too much, but it's still a bit better than what you had in the 2-dimensional space, which is to be expected because there's a lot more information which is preserved within your latent representation. All right. So ideally, we think of an autoencoder as this architecture where a 784 cross 1 vector is reduced, a dimensionality reduction happens, and you're getting a 10 cross 1 or a 2 cross 1 vector, right? But that need not always be the case. In fact, we can do the exact opposite. We can take like a 784 cross 1 architecture, input data, and increase its size to like 1200 cross 1 vector in your latent representation space, and that can then be brought down back to 784 cross 1 representation space. The reason for doing something like this is that we want to introduce something called as sparsity. Sparsity is something that we saw during regularization, L1 regularization, where we said that there is going to be a small number of kernels that we'll be able to use to reconstruct back the data rather than use every single kernel. So let's take this case where, these are essentially, we are visualizing the weights of an autoencoder trained on MNIST dataset. What you'll notice, if I zoom in a little bit, is that the weights themselves look like images. It might make sense because, as I mentioned before, these are kernels. These are filters that pass through your image in order to give you some results, right? So from a motivation perspective, I think it makes a lot of sense that the kernels themselves should look like the images. But there is an issue here where if I have, this one and this one, but let's say I have a different kind of a handwriting where I have I write my one in a curved fashion. This is not part of the template. So it's not going to always be able to reconstruct this image in the exact fashion because it's not able to preserve all information, right? If all your lines that it has learned are straight, it's not able to reconstruct this additional information that has come in, which is this kind of a slant. So what we want to do is reduce the redundant information in order to improve our generalization. So there is a lot of redundant information here. If you can see within the weights themselves, there's quite a bit of redundant information. So the goal is now to change that somehow. And there's a few ways of doing it, one of which is regularization, and another of which is changing the architecture itself. So currently, at least in this course, we'll be talking about the regularization part, since we have discussed that before, and there's a straightforward application for that. So whenever I say sparse representation, this is exactly what I mean. Instead of having a dense set of filters that is going to convolve or multiply with your image in order to get an activation, we'll have these sparse set of different kernels. So if you can see this, I don't know how much this is visible, but this looks like a 9. The non-highlighted regions, there's a small faint 9 there, but the most highlighted region is this part. And this here is part of a 7. This also is part of a 7. This is again part of a 9. And this is part of a 5. In other words, we are using 9, 7, and 5 in order to reconstruct this 7, right? So the reason we don't want this kind of weights to be learned is because when there is a small change, let's say this part, based on just the way I do, just the way I write, there's a small thing that comes in at the end of a 7. You want to be able to reconstruct this part as well. If you're always relying on a learned set of weights, you'll never be able to do that. But if you have more redundant set of weights, then there is a possibility that in some other number, this redundancy is captured. In this case, it was captured in the 9 part, right? So what you can do is, if this were a weight itself, you can multiply 1 with this particular weight, this portion here, plus 1 into this, the top part from a 7, plus 0.8 into this bottom part of a 7, and so on, right? So in different ways, because we have promoted this idea where it's not all based on a single number, like what it was here. Rather, it's based on a set of concepts of features within your weights, it is going to be better. At least that is the overall motivation that we are looking for when we do this kind of sparsity. Now, it's very straightforward that if we want to get these kind of redundant set of weights, we need more of these, right? How many of them are here? It's 1, 2, 3, 4, 5, 6, and I'm guessing it's about 8 here. So there's about just 48 weights that we have here, which implies that my middle representation here is going to be a 48 cross 1 in this setup. So if we want a more distributed or a sparse representation, we want to increase that 48. Maybe instead of it being a 6 cross 8, if this were a 12 cross 20, then the smaller set of weights or a smaller set of functions would be learned within each weight. Right? That's the simplest way of thinking about how we can reduce this kind of redundancy within each set of weights, which would imply that instead of this being 48, this would now be something like, I don't know what 12 multiplied by 20, I think it's like 240. Right? So now we are increasing this latent dimensional space. So in a way, when we discussed this before, a 10-dimensional versus a 2-dimensional, what is happening between a 10 and 2-dimensional is more weights are analyzing your image in order to get your outputs. So the simplest way of trying to get this kind of a sparse representation is just by increasing your the representation space Z. If X is 784, make this as 1200 cross 1. 784 cross 1, 1200 cross 1. So this will ensure that it is going to learn the smaller set of features within the weights that you can then use for your sparse representation within the network. Any question about the motivation itself? Yes.
So you're increasing the number of weights, but the idea is to decrease the amount of weights that are necessary?
Yes. And I know that seems counterintuitive. It's just that if I had a different number here, let's say an 8, right? None of these weights are going to be used for doing 8. There are 5 other set of these weights that will be used. If I had an 8 in a different handwriting, then the 5 weights that are used for the previous 8 will not be used later. So even though for a particular image, the number of things that we are using is going to be very less, the total number of basis functions that are required to represent it is much higher, is the best way of thinking about it. All right. So apart from the architectural change itself, there's a couple of other things that we need to do. And this part should be straightforward, what we had seen before. One is we can add some kind of sparsity constraint. So we're just talking about sparse autoencoders right now, in which case we need this kind of a sparsity constraint, and we've already seen this in regression. When we talked about regularization, we saw something called L1 regularization, where the goal was to construct this kind of a loss function, MSE, NLL, or any kind of loss function, and add this regularization on top, lambda into omega of Z. Now the sparse representation before, when we had it in the regression part, the sparse representation was on top of the data itself. But now we want our latent representation to be sparse, right? So that's why you do omega of Z. So the L1 sparsity is now based on the latent representation Z. So this is something we have seen before. If we want a simple, straightforward L1 sparsity, then it's just omega of Z, which is sigma norm of Zi, the L1 norm of your signal or your latent representation. So what it does is suppresses activations towards 0 to achieve sparsity. It tries to make sure that whenever you're reducing your loss function, which is something like this, it wants to make sure that the latent representations is as close to 0 as possible, or L1 norm here is as close to 0 as possible, which implies that each element within that latent representation should be 0, which is exactly what we want out of sparsity. This is something that we have seen before, but when we do this on the data, and when you have a small number of features, this is quite straightforward. L1 sparsity is quite straightforward. You've already even written functions using hinge loss function and some of the kind of L1 loss functions in order to achieve this, right? But when it comes to a larger architecture like autoencoder, this is not something that we can actually easily do. Constructing this kind of a L1 sparsity, it's a very harsh constraint. It's a very hard constraint. So what we would have to do in this particular case is try to not make it 0, but for it to come near 0. In many cases, what happens is that when we try to backpropagate this across multiple layers, since L1 norm is not differentiable at 0, we cannot construct a simple, straightforward function within PyTorch. What we would have to do is do an if-else function, which is exactly what you did back in homework number 2 when you were doing hinge loss function. You said if it's greater than the 0, then it has to be a certain gradient. If it's less than 0, it has to be another gradient. That is not easy to do when there are a large number of layers, right? Because it's all dependent on each other. So instead of trying to create this kind of a harsh constraint for sparsity, what we have is an KL divergence based constraint for sparsity, where we say that we'll have this kind of an L1 norm, which is, we'll call it rho cap. And this is nothing more than an L1 norm here. We're just adding your zi of j, sigma 1 to n. So basically we are adding every element within your latent representation. And then we want this rho j cap to be as close to 0 as possible. So this is where we add a KL divergence kind of result. Let me go to that formula actually, yes. So KL divergence is given by this kind of a formula. Where given your p of x, you want to construct in an alternative representation q of x that tries to mimic p of x as much as possible. So in other words, what we are doing is, instead of regularizing your z, we are constructing an alternative representation that we'll be calling rho, and we are going to say that the KL divergence between this rho and rho j cap, which is our sigma zj, is going to be 0. If we say that this is supposed to be 0, then rho equals rho j cap, and hence it's like this kind of approximation of sparsity based on an alternative representation. The distance between these two things, if it's 0, then that basically means that rho equals rho j cap. Hence, we are saying that rho in this particular case is, or rho j cap will go to 0. There are a few, we won't get into the details of KL divergence, but basically what you'll notice is that the minimum value of KL divergence is going to be 0 at a very, very low value. So which basically means that I can make, if this is equal to 0, then I'm saying that this has to be at the lowest possible value. But I don't need to make this 0 right now. I can approximate it, right? I can say that instead of this being 0, I can say this is 0.05, like a very small value. In which case what happens is that your rho j cap also will now become 0.05. So you have a little bit control over sparsity. In L1 norm, there was no control over sparsity, right? So you just had omega z and you had sigma of norm of z, right? So which basically meant that it either has to be 0 or it will be something else. It will be a higher value, which if applied within a loss function is going to be very problematic within your loss function. But now within KL divergence, what you do is you're restricting your sparsity to not be 0, or maybe restricting is the wrong word. You're not constraining your loss function to have a this sparsity constraint be 0. It can be something a little bit more than 0, which is more attainable. In these kind of large-scale neural networks, it's more attainable to have 0.05. And in L1 sparsity, there's no way you could enforce this criteria, but in KL divergence, you can. So this is a better way of enforcing sparsity rather than directly taking the norm and using that within the loss function. So the goal of KL divergence is we need some control over our sparsity, and also it's approximate sparsity. It suppresses activations close to a small value, not 0. It'll be something like 0.05, depending on what you set your rho to be. And most importantly, it's differentiable at 0, which essentially means that you can have a continuous function. Like if I look at KL divergence, this is how the function looks like. As you can see, there's no discontinuity anywhere. L1 regularization, on the other hand, has this kind of, since there's that modulus, right? So it always has to be something like this. This is how your L1 norm is going to look like, which means that here there is a discontinuity at 0. The limit from the left-hand side and right-hand side do not coincide. Hence, it's not differentiable at 0. It is true sparsity, however, which basically means that your activations are driven towards 0. But unfortunately, you have no explicit control over the sparsity. And sometimes in these large-scale neural networks, it does not train if you directly try to train using L1 regularization. So in terms of training, it's very similar as before. You have x minus x cap norm square and lambda into omega z. Omega z can come from L1 sparsity, or it can come from KL divergence. And this is how the results are going to look like between a fully connected. So by the way, you can do this regularization on any kind of a network, right? It can be a fully connected autoencoder or a convolution autoencoder. Either of those cases work. Or maybe either of these cases will work if you have a good regularization. And this is how the results are going to look like. I think it's very hard to keep track of what is what within this framework. The main reason being that whenever we train these architectures, whatever you had here will never be here, will never be here. This is the non-convexity of your neural network, right? So the same weights will not be within the same positions as they were before. And yet you'll get the same output. It's just that the positioning is going to be different. But in most cases, having regularization is going to help in the downstream tasks, similar to what we had with the regression and classification problems. And the visualization as well, it's very similar to what we had discussed before. If you have a 128 into 1 cross 28 cross 28, your weights are extracted and just shown as images. But these are nothing more than like these kind of fully connected weights that exist within your network. This was for nonlinear, and oh, okay, so this is for different lambda values, and you can see how the change in lambda value actually changes your result. So 0.005, so this is sparse AE L1, and this is, oh, okay, so this is KL divergence, and this is L1, my bad. So the difference between KL divergence and L1, usually L1 you'll see that it's more dispersed or diffused compared to the KL divergence results. Any questions about the regularization part? All right, next is denoising autoencoders. Now, we started off autoencoders by saying that the goal of autoencoders is to take an input and reconstruct the exact same input, and whatever is learned in between, the latent representation, is what is important for us, right? But there are different applications that can be constructed using these autoencoder architectures. The first one, and probably the most important one, was the idea of denoising within images. So if you have a corrupted input, in this case, hopefully you can see, it's a noisy version of 5. The goal of denoising is to get this kind of, you remove this additive white noise that we have corrupted our input image with. That is the whole point of denoising. And hopefully just by looking at the architecture, you should be able to see what the goal is. Denoising our autoencoder takes in an image which is corrupted, which has noise, and then denoises that portion in order to get back the original signal, which was the 5 in this particular case. So what we are trying to learn is a robust representation that undoes any kind of the effects of corruption that can exist. So in terms of the framework itself, we already, our assumption is that we have access to some kind of a clean image. During the training part, our assumption is this: we have access to some kind of a clean image, we have some kind of a noise generator, we add these two in order to get a corrupted input, and the goal is to get back the clean image here during the reconstruction portion. So during training, this is very important, where we need both the clean and corrupted image pairs. Right? So as you can see here, we want to minimize the loss function norm of x minus x cap whole square, which is exactly the same as our previous autoencoder. Like the normal autoencoder we saw last week was exactly this, which is x minus x cap whole square. Sorry, not last week, on Monday when we saw it. In other words, even though our input is the corrupted x tilde, we are still using our x minus x cap whole square within our denoising autoencoder. And if you see what the output needs to be, then it'll become, hopefully that will become clearer. We want our x cap to be x, which is our clean image, not x tilde, which is our corrupted image, right? So let's say you had a loss function which is x tilde minus x cap, and you were taking a norm in this particular case. Then that means that the output would actually reconstruct the corrupted input, which you don't want. What you want is to reconstruct the clean image. Hence, you are subtracting x, or you're taking the loss function between your clean image and your x cap in order to construct your loss function and to train your encoder and decoder architectures. Apart from that, it's exactly the same. Actually, in fact, the network and the training procedure is exactly the same. The only difference is that you are giving in corrupted inputs during your training procedure. But while actually doing the training part and getting the error, it's still the same loss function that we are going to be using within this denoising autoencoder. And this is kind of a motivation in terms of what is happening within the function. Let's say this is the best representation space. The one in black here is the best possible representation space of the clean input images. This is what your network should have learned based on clean images. But then you're given corrupted input images, but it doesn't matter. Even if the corrupted input is over here, you still want your clean image to be on this kind of a manifold. You want your reconstructed image as well to be on this kind of a clean manifold. So the goal in denoising autoencoder is that instead of creating a loss function between the corrupted and the reconstructed, if you create a loss function between the original input, the clean, and the reconstructed input, you'll still be able to get back this kind of a manifold. So this is what a denoising autoencoder essentially does. It tries to learn a robust representation even when you are given this kind of a corrupted input x. Any question in terms of the architecture itself? Yes.
That graph, can you explain what the one before it?
This one?
So it's trying to map it to that line?
This line, so the word manifold is something new which we have not covered, but manifold is essentially just this kind of a subspace within a larger dimensional space. So let's say our Z has a representation of 1000 cross 1, right? In order to visualize this, we need a 1000 dimensional space, but we are restricted to a 3-dimensional space. So whenever you see these kind of representations, we bring it down using PCA to 3 or stuff like that. What we have noticed in these cases that is there is a regularized structure within this 3-dimensional space or a 2-dimensional space, which implies to us that within a 1000-dimensional space, there is also a regularized structure. There is probably like a 20-dimensional space within a larger 1000-dimensional space where all your data is going to reside in. In other words, the other 980 dimensional space are not as important in this context. So this 20-dimensional space is what we call the manifold, and the original image, the hope is that the clean images lie in these 20-dimensional space. The corrupted images move it from a 20-dimensional space to a 23-dimensional space, let's say. It adds 3 dimensions based on some kind of a noise thing that we are adding on top of it. The goal is to remove those 3 other dimensions in order to come back to this kind of a manifold. So it projects back into the original manifold that was there before. All right, so the results of a denoising autoencoder. So you can see here, the top one is the input images. You can see that there's some kind of a noise that has been added to all these images. And when you pass it through a learned denoising autoencoder, this is what the results is going to look like. So this is for a nonlinear activation. This is for a linear activations that are there. In many cases, it's very hard to see the difference between something like 0.06 and 0.03. I think last time we had seen like 6 and 6, right? This 6 is a little bit blurrier compared to one on the right-hand side, which shows you that non-linear activations is something that you need to aim for within the autoencoder framework as well. So with that, we move from denoising autoencoders to variational autoencoders. So there's a lot of stuff within variational autoencoders that we are not going to go through, and which is not going to be there on your quiz or your homeworks, but it's very important in terms of trying to understand the new landscape. At the end of this, we'll basically show visualizations where we'll be generating novel samples, which is essentially what your generative models are. Whenever you go on ChatGPT and ask for a new image, whenever you go on DALL-E and input a prompt, a text prompt, all you're doing is this kind of some kind of an extension of this variation models, or variational autoencoders, which are currently the diffusion models. So understanding something like denoising autoencoders plus variational autoencoders is the most important part of the diffusion models, of stable diffusion and everything that exists currently. So let's start with like a motivation for what variational autoencoders are. So we have seen until this point that autoencoders reconstruct the input data via some deterministic process. Of course, it could be like a noisy version of the data, but even within the loss setup, right, we always had x minus x cap. So we are still reconstructing the original input image throughout this particular process. The goal in variational autoencoders is to generate some kind of normal samples that was not there as part of the training data. If it has trained with 10,000 or 60,000 MNIST images, can it construct a new image within the MNIST dataset that it can take and say that it's very different from all the training data that exists? So this is when we use the word generate, this is where the generative AI part comes from as well. That whenever we say generative AI, that means that it has not seen that exact input before in its training regimen, and this is something new that it is coming up with on the spot. So in this case, the image that we are showing here, you started off with a 7, but then you'll end up with a 1. There is a process of constructing this ones essentially based on the 7s, and we'll be discussing on what that is. When we discussed about autoencoders like on Monday, we said that if it exists within this kind of a green region or within this kind of an orange region, it's able to reconstruct, right, 5 or 7 because it exists within those regions. But then there is this one portion here which is in the middle of both these clusters, which the network does not know what is there. It's a region within its representation space that it has not explored before. In other words, it has no previous training data in this particular region, and the output is going to look something like the closest nearest neighbors, let's say 5 or something like that. There is a discontinuity essentially within this kind of a Z representation space when you have trained it based on 60,000 images within your MNIST. So what happens then is decoder generates an unrealistic output if sample generates, if there's some example within that region during inference time. The goal in a variational autoencoder is that we want to create a more smoother representation space. Instead of having just plotting these points on our representation space, what we do is we construct this kind of a probabilistic distribution that is going to cover every single region within your representation space. In other words, what I'm saying is that we say that there is already a probabilistic region that exists within Z, and the goal of an encoder or training is to populate that representation space, is to populate that distribution rather than constructing that distribution. So that statement will hopefully become more clearer in the next few slides. But essentially that means is that Z is drawn from some probabilistic distribution. within this representation space rather than constructing this representation space. Until this point, we have just constructed Z based on an encoder, but now we are saying that Z exists irrespective of whether you have an encoder or not. Z already exists in this form. The simplest, so when we uniformly sample Z, the decoded images vary with smooth transition, which implies that if I'm taking some point here, some point here, some point here, it doesn't matter. There's a smooth transition from 5 to 7 that you can see within this particular framework. So for this, we need some kind of a probabilistic perspective on what Z is going to be. So to generate this kind of output, X cap, let's start by thinking of Zi, which is an instance of your representation space. And by instance, I mean a single point. This can be something like a Zi. It is sampled from a probability distribution, P of Z. So P of Z in this case is a prior distribution. Again, these words should be familiar to you from when we did the GMMs and logistic regression. It's basically a prior distribution that already exists. In the beginning, we have no idea what this probability distribution is. We'll take a very simple Gaussian distribution. After that, we do this kind of expectation maximization plus MLE in order to get a better representation of this Gaussian. That's exactly what we did in GMMs, right? We solved for your mu and sigma, and that is exactly what we do in variational autoencoders as well. So let's start by saying that we, given some sample Zi given Pz, we draw Xi cap given P of X cap given Z. So X cap conditioned on Z basically. That is, think of this as we have no encoders at this particular point. We only have this Z. And based on the fact that we know that Z is a probability distribution, we can take some instance of this particular Z and we can get back a X cap because we have a probability distribution, a posterior distribution, X cap given Z in this particular case. So this is the probabilistic modeling we want, essentially. P phi of X equals some integration of P phi of Z multiplied by P phi of X given Z, where Pz here is some kind of a prior, and we have conditional distribution at the end. So while we want to do something like this, the simplest way that we started off within GMMs, we'll do exactly the same here as well. We'll choose prior to be some kind of a Gaussian, which is some normal distribution with mean 0 and identity matrix as our covariance matrix, which is basically just a diagonal of 1s. Everything else is going to be zeros. Again, this is exactly what you did within GMM framework. And our conditional P of X cap given Z is quite complex, which is the output over here. Based on a very simple distribution at our input, we need to get a very complicated set of images, right? So whenever you input something within DALI, you're expecting a good-looking image to come out of it. So there has to be a complex decoder architecture that should take this kind of a sample from a normal distribution and convert it into a very complicated set of images. And we'll use a neural network decoder to construct this kind of output. So this is a simple Gaussian prior, and this is a decoder architecture. Your phi is a decoder architecture. And the way we do phi is by maximum likelihood of training data. Again, exactly same as we had in GMMs. We'll use MLE in order to get our GMMs within the framework. But it's not as simple as GMMs. The problem being that this kind of a P of X given Z, as well as P of phi, is intractable. We don't have access to all possible data within this kind of a distributional framework that will help us create this prior. We don't have access to all possible sample conditions as well that will help us create this prior. From a motivation perspective, think of the size of the features that we are looking at, right? Let's say our decoder, our latent representation is something like 64 cross 1. That basically means that there are 64 dimensions within your Z. So if you're constructing a GMM based on 64 dimensions, then even in a single dimensional Gaussian is very easy. right? It was something like this. In a two-dimensional Gaussian, it is going to be something like this. And in your exam, I think you saw 2 dimensions was, okay, this is what the elliptical curve would look like in terms of the 95% confidence. Think of this exact same thing in a 64-dimensional framework. It is not easy for us to construct a 64-dimensional GMM or some kind of a Gaussian model based on the amount of data that we usually have, because we need to construct this kind of a covariance matrix where we need the distributional correlation between every single element, or not element, but between every single dimension within your C. So we start off with 1, 1, 1, 1, 1s and zeros everywhere, but after that it is very hard to populate something like this based on the fact that our P is P of Z is not it's intractable. Getting an integration of this entire thing is intractable. So posterior density is also unfortunately intractable because of the same reason. We don't have enough data, or there is no way that we can sample every single point within this continuous distribution in order to integrate it and create our P phi of Z given X. And this is where we start by saying that we need an encoder back. So until this point, we have only looked at the decoder part and said that we know that Z is a probability distribution that exists already, and we are sampling from that Z. But now we are saying that, okay, it's not possible now to, it's intractable to consider Z on its own. So we need some kind of an approximate posterior. So we are thinking that maybe if we have an encoder, we can construct another distribution called Q theta of Z given X and use that in order to construct our output. So again, it seems like we are back to the point of where we started, which was an autoencoder, where we have an encoder and then we have a decoder, but it's different. Our assumption that we started off with is that Z is independent of this particular X, or we don't care about X while constructing our Z. I shouldn't use the word independent because it's not, but our hope in the beginning was to state that Z already exists and we don't need an encoder to populate it. But now we are saying that we need an approximate distribution Q that is going to approximate our P of Z in this particular case. Your Q theta of Z given X is going to exist, that is will be used to construct P of Z. Any questions until this point in terms of what the difference between variational autoencoders and normal autoencoders are? Yes.
So we need to have some kind of assumption about Z and like the number of classes or clusters.
No, there's no assumption about the number of clusters. There's an assumption about the dimension itself. So if I know that it is a 64-dimensional latent representation space, then the mean, where do I have? Yes, the 0 will be a vector of 64 zeros, and then your covariance matrix will have 64 cross 64 with 1s in the diagonals. There's no assumption in terms of class, cluster, anything. There's no concept of a class in this particular case. It's completely unsupervised. So prior, in this particular case, the prior is for Z. We are saying that there has to be some kind of prior for Z. In classification, it's more easier to understand because in classification, the prior is going to be 1 divided by n, which is the number of classes that exists, which is that the probability of all classes is the same. In this particular case, when we say that the assumption is n0, 1, then that means that the latent space is distributed around 0, which is the mean. If there's some kind of an axis in the 64-dimensional space, it's surrounds 0, and all dimensions are uncorrelated with each other, like the simplest assumption that we can make, and every single dimension is exactly same compared to the other. That is the main assumption that we are making. But maybe I can show you the very last slide to make it a little bit more clearer. So let's say I have 2 dimensions, so Z1 and Z2. Our goal and our hope is that Z1 and Z2 essentially controls different parts of the image itself. So in this case, if I vary Z1, you'll see that it's moving from 1 and it's changing a little bit its orientation and moving towards 9. If I vary Z2, it's moving from 1 in this case and 0. If I vary Z1 and Z2, which are all these regions here, it's changing into other things. So in this case, the prior is not based on the class, but it's based on certain features or elements within the image itself, the patterns within the image itself. That's the goal essentially. Any other question? All right, so the next few slides, maybe I should have maybe I'll re-upload the slides by saying that from this point onwards, 31 to, before we meet elbow. Yes, 31 to 38 is just FYI only, so we won't be covering that. The math portion of this is quite tedious, and it's not as important from a fundamentals course. So you'll have to take my word for it that this particular, I have this incorrectly. So it's elbow, this is evidence-based lower bound. So this is evidence lower bound, elbow. I've written it as variation lower bound. That's very restrictive. Elbow is a more common terminology, which is evidence lower bound. So I'll re-upload the slides with this. And everything from 31 to 37 is just for your reference only, that you can look through later. But you need to now take it on faith that if I want to construct this kind of a variational autoencoder, the loss function that I need to minimize, or in this case, we want to maximize our elbow, is going to be this, the equation on top. It has two terms. The first term is just reconstructing the input. Your expectation of log P of phi x given z. X is basically the input that we had, or xi is the input that we had. So in order to construct this kind of a decoder, we are just reconstructing the input that we originally had, and we're using that as the first term. The second term is we have q of theta, which is our approximate posterior with p phi of z. We are taking like a KL, dKL is essentially your KL divergence distance between q theta z of z given xi and p phi of z. Notice that p phi of z is not dependent on x, it's not conditioned on anything, while q theta is conditioned. Q theta part is the encoder here, while the phi part is the decoder. Right? So what we are looking at within the framework is still an encoder and decoder architecture within a variational framework. But what we are specifically doing is we are putting a KL divergence between a distribution that, between an approximate distribution, which is q theta z conditioned on x, with let's say the true distribution, the interactable distribution, which is p phi of z. The second one is actually, so make your approximate posterior distribution close to a tractable prior p phi of z. Example, some kind of a Gaussian. We start off with this kind of a Gaussian, and we try to make it as close to it as possible. And that's exactly what we saw when we showed KL divergence before as well. So it's essentially we are making the left-hand side same as the right-hand side. We are trying to make it as close to 0 as possible, so that this entire equation, or this entire equation here, is going to be maximized. That is our goal within the variational autoencoder framework. While doing this, the output we are kind of getting is exactly as a GMM, where if you remember the expectation maximization and MLE step that we were going through, what we were doing, we're estimating the mu and estimating the sigma. This is what we are doing. Again, the goal is to say that Z is a distribution, a Gaussian distribution, and a Gaussian distribution can be characterized by just two numbers, which is the mean and the covariance matrix. Not two numbers, maybe by two parameters, which is the mean and the covariance matrix. So based on the fact that we have an X, our encoder is not getting a representation right now, but rather it is getting a distribution. And this is very important. Right? In a normal autoencoder, we just map it to a deterministic representation space. But at this point in variational autoencoder, we are saying that all data is being fed in order to construct a distribution, and that distribution is parameterized by mu and sigma. And when it comes to the decoder side, I can now sample anything from this mu and sigma. It doesn't have to be the exact input that we had before. So this is the major difference between an autoencoder and a variational autoencoder, or a simple autoencoder and a variational autoencoder, where a simple autoencoder has a deterministic process that the input will have a deterministic z, while in a variational autoencoder, the input will construct this kind of a posterior, the approximate posterior distribution that is parameterized by mu and sigma. Across backpropagation, it's exactly similar to GMMs, where we'll be updating our mu and we'll be updating our sigma in order to get the best possible representation within this kind of a latent distribution. Any questions here? All right. So again, now the goal is that if I want a new z right now, all I'm doing is I am going to be taking something, or I'm going to be basically sampling something from this mu and sigma, and I'm going to get a z. Now I can use that z in order to construct my decoder and get back, or not construct, but basically decode it into a new sample that it has never seen before within the training distribution. So z is not directly computed by VAE. It basically is sampled based on the encoder architecture that we have in this case. So this is exactly the same. The decoder also follows a similar process. Since z is not computed, it is essentially something that we are taking from the previous encoder. You're getting a mu and a sigma. We are sampling both of them, and we're using them to reconstruct our x cap in this case. So from a far away point of view, if you look at a variational autoencoder, it looks very similar to that of a normal encoder. But when you take the implementation point of view, this is how it looks like. You have this block and this block that is different from a normal autoencoder. That creates the major difference. Again, the underlying assumption is that z exists already, and the encoder is just helping us parameterize the z based on some approximate posterior, which is q theta of z given x, essentially. This is all that a variation, this is the most important part within the variational autoencoder that is being constructed at this stage. Any question about the inference part, where we just sample your z in order to get some new output that is going to be x cap in this case? All right. So there is one issue that we can't simply neglect within this particular framework. In GMMs, for instance, it was a procedural process, right, where you knew that there was an MLE and then there was an expectation maximization step, and both these steps together would form your final output. But in this case, when we are trying to use backpropagation in this large framework, the issue or the problem with this entire thing is that your z here, we are considering that to be a random variable. We have a distribution, a normal distribution, from which we are sampling our z, which implies that our z is random. That essentially means that if you trained an architecture and I were training an architecture with exactly same weights to begin with, then the z that you are choosing will be different from the z that I am choosing. So there's no way that backpropagation is going to give us the exact same result. It's not we are trying to use a deterministic process within a random variable setup, which is not possible. So instead, what we have to do is, so in this case, we cannot backpropagate through a random variable z. There's no way that you can, add or subtract something to z or use some kind of a differential of z of a random variable to get your output. So what we do is do something called a reparameterization trick, where instead of considering z of x to be some kind of a random variable, we are saying that it's mu plus sigma. This basically is just a simple multiplication, just an element-wise multiplication. It's called a Hadamard product. And based on this, we are just multiplying it with an epsilon. And this epsilon is something that is deterministic. We start our training process by knowing what this epsilon is going to be, right? So, sorry, this mu is the random node in this particular case, which implies that we have our x and phi are something that already exists. In this case, this will be your decoder architecture, and x is the input that you began with, which is where your input is coming from, or your encoder architecture. So your epsilon in this case is controlling the randomness within the variable, and you won't be changing that. It will remain exactly as is, but you'll be changing the decoder, the encoder part, which is where your theta and phi is going to be coming from. So it's nothing more than some kind of a normal distribution that is given by 0, I. This is something that we have seen across regularization as well. Sorry, not regularization, regression, where we use this kind of a noise setup within our x transpose plus epsilon. So if I were to construct your variational autoencoder on this kind of a MNIST setup, it would be very similar to what we did before, except there's going to be two different, this part here is going to be different from a normal autoencoder, where we have this kind of output that we get from the encoder, and instead of sampling saying that z itself is random, we have a random variable. A sample is nothing more than a normal distribution that we are getting 0, 1. In other words, what we are doing is we are just sampling noise, adding the encoder image, and then passing it through the decoder. That is essentially what reparameterization trick has done here, which is this kind of a sample epsilon. Our sampling is just random, but then the output of our encoder is what is constructing this kind of a non-random generation of our input to get whatever output that we need. So this is kind of the outputs that we can expect from VAEs. If our goal is to simply reconstruct it, VAEs can do that, similarly to before. So in this case, you can see that every instance 8, 9, 0, 1, you get back the exact same numbers within the reconstruction framework. But the importance of VAEs is in constructing this kind of a randomly generated new images, which the network had never seen before. So in this particular case, when we train it, on the right-hand side, these are images that the network has not seen within its 60,000 images in the training set. Now, the way we know that this is not seen, the way we know that this is not seen is that we need to construct some kind of metrics. In natural images, there's a lot of metrics that are available in terms of quality, aesthetics, where we can say that one image is not retrieved from your training set when you're constructing it. It's a little bit more harder to construct these metrics on something like MNIST, which is very simple, but something like an MSE, between reconstructed, let's say, this one image and all 60,000 training images, if the mean square error is greater than a certain threshold, then you say that this particular image is new. It has never been seen before. That's something that you can get out of it. But essentially, based on these metrics, you can now state that all images that occur within this, I guess is 10 cross 10 block, across this 100 images are new, or it has never been seen before in the training data set. So this is what we would call a novel sample, and we don't need an encoder at inference, right? Because our original assumption was that Z is a random distribution. It's just that we couldn't train it. Not a random distribution, sorry. Z is a distribution that already exists. Since we could not train our decoder, since it was intractable, phi was intractable, that is why we had to come up with all the Q parts within the training setup. But at inference, you really don't need any kind of an encoder. You're just randomly taking an epsilon and saying that based on this epsilon, I can now construct our image. Again, you don't need reparameterization trick in inference because there's no backpropagation. So all this part does not matter. Just this directly goes in, and you're just randomly picking an n comma I based on a n comma I in order to construct your new sample. This part I'd shown before, but usually the goal, this is something called disentanglement. So there is research direction that is called disentanglement. where some properties within your input data needs to be changed. Like whenever you say, you can go to ChatGPT or DALL-E and say that construct this painting based on, if it's Da Vinci's painting, you can take that and ask in a different style, right? So that's a certain property within both artists that exists within all their images. And if you want to change that, then you want to disentangle all your Z's essentially. So maybe this Z is looking at orientation, let's say. And Z2, if we just have a two-dimensional Z, the first Z is looking at the orientation, the second Z is looking at, I don't know, like major classes, like horizontal distances within these classes, which is going to help us create multiple classes in this case, right? So I'm just going to call this as classes for now, but there's no concept of classes, it's more the distance. It's changing a small value within your Z2 is going to change your class essentially. From 1 it becomes a 7 to 9 to 4 to 8 to 5 and so on. So this is essentially what we want from our VAE, where each of our elements Z1, Z2 to Zn is going to be disentangled from each other. If Z1 controls one property, which is orientation, Z2 is going to control another one. So when you prompt it, technically, when you say that you are changing your Z1 between what you have to something else, then you can get from 1 you can get a 9, or you can get an orientation from a left-sided orientation to the right-sided one. Same thing with Z2 as well. When you change something else, you can get a different kind of element. That's where the idea of prompting comes from. Again, the idea of VAE, the elbow part, which is the evidence-based lower bound, has existed since 1992, but VAEs are quite new. It came out in 2015, but since then, the amount of changes that has happened is quite a lot. So obviously, we are not going to cover anything newer like the diffusion models that exist, but if you were to study diffusion models, it's exactly the same. The math portion is going to be exactly the same as VAEs. It's also going to construct and consider denoising autoencoders as well in order to construct new images. I think I have, so this is the end of the lecture, but let me just show you in, all right, so last year in CVPR, they had a very good tutorial on diffusion models. If you just type in tutorial on diffusion models and go to CVPR 2023, it says 24, but it was in 23. If you go to their project page, the first part 1 is an excellent resource in terms of what diffusion models are, and they go through the exact process that we did in terms of evidence-based lower bounds. But in diffusion models, it's just a forward and a backward diffusion model, where the forward is instead of going directly from your image space to some kind of a random distribution, which is nothing more than noise, they do it in this kind of a stable fashion where it's done one on top of the other in order to get to the last stage here. So it's not, of course, there's a lot more bells and whistles for you to move from variation autoencoders to diffusion models, but the underlying math is still the same. In fact, there's a lot more of the unit architectures and results that exist over here. Yeah, if you just go through, even before the outline, it shows you exactly the differences and similarities between like variation autoencoders and these kind of diffusion models. Again, that part is not something that we are going to be covering in the course, because this is again a fundamentals course, but there is a linear relationship between what we have learned to the state-of-the-art existing modules out there. But that is the end of autoencoders. From next week, we'll start with sequence modeling and hopefully come to like transformers by the end of next week. Thank you. By the way, I'll re-upload the slides. Between 31 to 37, it's not required. So it may not be essential to put that there.